Hello, good afternoon, everyone. My name is Paris. I will talk to you about multi-modal stress response modeling in competitive League of Legends. I'll give you an outline of my today's talk. I'll talk about motivation and design criteria on this study. The study revolves around the data set. Is there something wrong with the cable? Is this flashing for? Okay.
Yeah, but
okay.
it seems to be fine.
Okay. This paper revolves around the data set that has been collected. I'll show you some visualizations of the data set, and I'll talk about what can be done with it and a bit of future work. So about motivation, what we want to do with this data set is study the effective aspects of competitive gaming. And in order to do that, it's impossible to do that by using those large-scale data sets that appear online, which only include game data. So we had to collect the data sets ourselves to create a player-centered eSports data set. There's a few design criteria on how to collect a data set like this. First of all, we want to monitor the tacit player reactions, so what you don't see in the game when watching it as a spectator. We needed the physical presence of the players in the data collection room, in the game room, so that we could directly collect the data from them, and we also needed the players to be playing in a competitive environment. So taking the criteria in reverse order, I will talk about competition first. We chose competitive games because we assume that competitive games should have an effect on players' affective state. We collaborated with TSEA Link Rupees. TSEA stands for Tilburg Student Esports Association. For the University of Tilburg has an esports association where students have teams in League of Legends, Heroes of the Storm, CSGO, Dota 2, a lot of games. So their League of Legends team is called Rupees, and they participated in the Dutch College League, which consists of 11 teams around various universities of the Netherlands. The Dutch College League is played on a weekly basis, and every week each team is assigned an opponent, and they play two games against each other, switching sides in the middle. So first game, team one is blue side, second game, team one is red side. To ensure the physical presence of players, we used quite new Tilburg University Game Lab. It's what you see in the picture. The University Game Lab has 10 high-end, high-performance computers where players can play the competitive games. They bring their own peripherals to feel comfortable, and they basically reserve the room for a few hours to play their competitive games. This room enhances or fosters team environment, so instead of having every player play from their home environment, we gather them all together into the game room, and they spend those hours playing, and that enables us to do the direct data collection that we want. And what is this data collection? In order to monitor the tacit reactions of the players, so the unseen reactions, we decided to collect data from mouse and keyboard activity using the RUI, that's the software on the left side, which collects all the key logs, all the mouse clicks, and all the mouse movements that a player does on their computer. We decided to use physiological sensors to collect heart rate and skin conductance information during gameplay, and we also decided to use in-game data from the Riot Games API to combine the tacit monitoring modalities with the in-game modality. So how does the data set look so far? We have 8 players who belong to the TSEA Link League of Legends team. 7 of them are male, 1 female, 21.5 years old with a standard deviation of 1.6 years. And I should note at this point that none of them is a full-time professional League of Legends players. All of those players are still students of the Tilburg University. They're around high platinum, low diamond ranking, and they decided that they can form a team and play in the Dutch College League. So I wouldn't call them full-time professional League of Legends players. A rough overview of the data set. We managed to collect data for 8 out of the 10 rounds of the DCL. That's because the lab was not set up exactly when the DCL started. And for 3 out of those 8 rounds, we have sensor data. That's also because we didn't have the sensors available from the beginning. So we have 6 out of 8 players. Of course, there is 5 players starting in a League of Legends games, but we have 6 out of those 8 players who participated, providing sensor data to our data set. And if you look at the table, you can see the 8 different players, how many games each one of them played as a starting line in the starting lineup. You can see roughly the mean APM that they had, keyboard and mouse-wise, heart rate and BPM and skin conductance in micro-Siemens. In order to use a data set like this, pre-processing is necessary because the various modalities that we're using are completely out of sync. So they have different sampling rates. They are collected in different time zones. For example, the Riot Games API data belongs to this time zone, to the UK time zone. But if you're located somewhere else, like we're located in the Netherlands, you have to pre-process the data to synchronize the time zones, for example. And also, different modalities have different computational requirements. For example, physiological sensor data is gathered raw from the physiological sensors, and it has to be transferred to informative features in order to be used. And, well, not to jump BioSpy, but BioSpy is a Python library that enables easy and fast processing of raw heart rate and skin conductance signal. So raw data looks like this. On the top left, we have keylogger data. There is a timestamp in string format. There is the action, what happened, left mouse click, for example. There is X and Y coordinates. Every mouse move is tracked. On the bottom left, we have physiological sensor data. The timestamps are in milliseconds. So it's a double in terms of computer language. Then there is all the features that the sensor can track. So there is accelerometers, there is gyroscopes, there is skin conductance. And on the right side, there is Riot Games API data, which is a minute-by-minute screenshot of what happens in the game. So Riot Games doesn't provide a second-by-second or a really detailed overview of what happened in the game, but instead, every 60 seconds, you have a table of events, of what they consider important events, such as placing wards, leveling up, champion kills, tower kills, elite monster kills. So I'll give you an example of how I pre-process this data. I set a custom interval time at 500 milliseconds, so I had to sample each modality every 500 milliseconds in order to extract important features or descriptive features and create a unified data set using those timestamps. And it looks something like this. So on the left side of this table, we have the timestamp. Every 500 milliseconds, I collect the player's HR, which is sampled at 20 hertz, for example, when the raw signal is acquired. So it's down-sampled to 2 hertz. Same for skin conductance. APM for mouse, APM for keyboard. Those don't have a sampling rate, but every single action is tracked by the RUI, so I have to aggregate over half seconds. And then there is binary variables such as kills, assists, deaths, building kills, and elite monster kills, which is basically a sparse matrix of zeros with occasional ones whenever one of those things happen in game. And this is for each player, for each game. And visually, it looks like this. So this is one game's and one player's APM during a competitive League of Legends game, annotated with important events such as kills, deaths, assists, buildings, and elite monster kills. You can see how the APM fluctuates during a competitive game. Same for heart rate. You can see that the heart rate starts at approximately 80, can go as high as 130, depending on what's happening in the game, and at some point the game finishes. And same for skin conductance. And this particular example is interesting because you can see that the player started playing the game specifically as, I would call him highly aroused or stressed, or, well, let's say aroused. And when the game finished, and this game was a win, he was clearly less aroused than he was when starting the game. There is some limitations when collecting and using data sets like this, particularly those shimmer sensors that you saw in the picture. can make the players feel uncomfortable. So we started with the players wearing those sensors on their keyboard hand. Those sensors have finger straps that you use to have the electrodes attached on the fingers. The players asked me if they could transfer to the mouse hand, because the mouse hand doesn't have too many individual finger movements. But still, sometimes the players reported off the record that the sensors feel a bit uncomfortable when using them. And also moving your mouse or keyboard or whatever hand can cause significant movement artifacts and noise in the sensor data. Regarding stress response modeling or stress response monitoring, we recognize that player stress levels or player arousal can be affected by multiple factors, not only the ones existing in the data set. Player stress can be affected by inter-team relationships, let's say. It can be primed by whatever the player is experiencing in his real life. And lastly, Riot API doesn't provide all the necessary data that we would like to have. Riot API provides limited data. As I said, only 60-second screenshots of the game. Also, when competitive League of Legends is regarded, players have to play custom games for which Riot API doesn't provide in-game data. So we had to set up a mechanism to generate tournament codes and play through those tournament codes, and then tournament games have even less data that we can use. What should be added in this data set to make it even more valid should be baseline measurements, which I haven't collected so far, but I definitely will. This could be in rest situations or in casual, non-ranked or non-competitive playing. TSEA Link promised to play in the next season of DCL, so hopefully we're going to get more players and more data to enrich the data set. And maybe we could add some more sensors to monitor the players, some maybe less invasive ones than the physiological sensors on the fingers, such as webcams or eye trackers. And a bit of future work. What we plan to do, first of all, is a feasibility study. Can we create models of players' effect with the given data set? If we can, what do we want to do with it? What exactly are we going to model? What features are we going to use? We could develop a real-time monitoring tool for player effect during competitive games. We are actually, at the time being, working on a real-time monitoring tool of player effect, which is going to be used in serious games, but we could transfer this to the eSports side. And a bit of a far-fetched idea could be, instead of only focusing on player effect, could be a performance or player focus or player mechanical or soft skills tracking tool. So this could be used for other studies except effective player modeling. The data set is available for download in this link. If you want to take pictures of this, I'll just leave it here. The data set's fully anonymized and obfuscated, so no sensitive data is available online, like player passwords, for example. And if you need more information on the data set, you can contact me directly through this email address. Thank you very much.
There's a couple minutes for questions.
Go ahead. Yes?
So, I might have great talk, by the way.
Thanks.
I might have missed information. Does your data set contain annotations, labeling of some sort, or is it gameplay data plus heart rate and speed of that?
You mean manual annotations by me or by some expert?
By anyone, yeah.
No, it doesn't contain any annotations.
So how do you plan to do player effect?
Well, personally, I would think that personalized models would be the best way to go. If I gather baseline measurements for every player, I can see in different situations what their effective state looks like in terms of sensor data, or let's say APM or keyboard or whatever sensor, whatever modality. And then based on that baseline, I'm not sure whether I can specifically give labels to certain states, like highly or moderately or not not stressed or whatever this label is going to be. But I don't necessarily think that having labels for states is necessary.
Okay.
We can discuss that further, of
Sure,
course.
let's do that, because affective computing, the whole field is built on the fact that you need some grounds with labels to predict.
Yeah, well, there is an expert rating in the League of Legends as well. You can use that. It's like the final rating that the game provides at the end, for example. That's one thing you can use. Or
And
you can find a statistical model from this data, and yeah, go from there, or just ask experts to make data sets.
or you can even, or you could even ask the players through questionnaires. But again, the question is, do you trust the questionnaires? So can players report their exact feelings within gameplay? And of course, you don't want to interrupt the competitive game while it's being played. Please.
I do actually agree with what he says, especially for construct like stress. It's very elusive and
Do you agree with me or with
yeah,
me?
with like, I guess it's different from emotion, and you can much more rely on physiological data, and especially on a comparison between the baseline. And if you go with a label, you should say someone is stressed, while if you only rely on physiological data, you can say someone is very activated, and then infer the reason from the gameplay.
Yes. Yeah, I agree with what you say. Of course, I think you have a point as well. But imagine this, if we think that there is an optimal stress level where you are at your peak performance, then if we are able somehow of finding this optimal stress level for the individual player, right, in a personal setting, then we might not even need a label. We just have to find a function that maximizes or minimizes towards that specific value of skin conductance.
Is there a presenter for the second paper? You can answer one more question and then...
I just have a very simple comment. We're in grade lab, are next to you guys, and we have a different type of skin conducting system, and
Yes.
we have web systems to capture the emotion of the person. Let's talk afterwards.
Yeah, sure. Yes. Thank you.
Thank you. Katona. Ready for it?
Yes.
Okay, the next speaker is Adam Katona from the University of York, and he's going to present the paper Time to Die. Please go ahead. I will signal 5 minutes.
Okay. Thank you for the introduction. So I'm going to tell you about the model we created to predict who will die in Dota 2. So this work was done with collaboration with Ryan Spick, and there were many other people who contributed it. We are part of the IEEE group from University of York. So to those of you who haven't played Dota 2 yet, it's one of the biggest eSports title, and it's about a 5 versus 5 game where each player controls a hero, and they use their abilities to level up, collect gold, and eventually destroy the opponent's base. This game can be really complex, and commentating a tournament game can be a really difficult job. So these are some discussion from a Reddit thread where people were discussing their favorite commentators, and from this you can see that even experts struggle sometimes to follow every action in the map or pay attention to every important aspect of the game. And rarely it even happens that the commentator team misses the big fight which decides the game. This happened 2 years ago when in a big tournament there was some parallel action, and actually the commentator team totally missed the big fight which decided the game. But why is it so hard for humans to understand this game and follow it? So it has several properties which makes it difficult. First, it's really fast-paced. The game state can change in a fraction of a second. Also, there are lots of variables. There are more than 100 heroes. Each of them have different abilities which interact in a complex way. Sometimes they synergize, sometimes they counter each other. So there are a lot of things to consider. And also, it's played on a relatively large map. So many things can happen in different locations. So it's really hard to pay attention to every location at the same time. But if we think about it, computers, these kind of properties are not difficult for computers. A fraction of a second is a very long time for a computer. It can evaluate a whole scene in milliseconds. Also, it can keep track of thousands of variables easily and calculate with every little effect. Also, it can focus on every location at the same time. So it would be really nice if we could use computers to aid the job of commentators. So the ideal goal would be if the computer would predict where an exciting event will happen and point the attention of the commentators to that location. But this is really hard to measure. So instead we can have a proxy goal of predicting where will the next death happen. And this is not quite the same, because sometimes there are some interesting action where nobody dies. And sometimes, even when someone dies, it's not so exciting. But in the vast majority of cases, when someone dies, it's exciting and we want to pay attention to that. So we can frame this as a machine learning problem. We can try to predict, we can select a window of, for example, for 5 seconds, and the model can predict whether a player will die in these 5 seconds. So we can think of it as a binary classification. And we have 10 independent outputs because we have 10 players. So we collected a large amount of games. We had 7,000 games, which resulted in a data set with 80 million points. And that's one nice thing to work with games, is that it's really easy to get a lot of data. And we open sourced our code to generate this data set and for the project. So if you are interested in working with this kind of data, it's on GitHub. And for the input features, we have several features. For example, the health of the player, the mana, the abilities, the cooldown on their abilities, the position of the towers, the health of the towers. So it's really, you can look at every little variable in the game. So for our model, we used a multi-layer feed-forward neural network. And we used a few tricks to make it more suitable for this problem. One of them was weight sharing. So weight sharing is most widely used in image processing, where you have a convolutional network. It applies the same weight for different patches of the image. And this is really beneficial because you have this inherent symmetry of the problem that the object can be any part of the image, and you still want to calculate the same kind of abstract representation of the data. And because you apply the same kind of computation, you can fuse data coming from different parts of the image in this abstract representation space. So we can do the same trick with our death prediction network, because we have 10 players, and each of them have the same kind of features. And there is this player slot, is the order of the player's login. It's not really important. We want to calculate the same kind of features, whichever slot the player is in. And with this, we can combine the data from different players in this abstract representation, which is much easier than if we look at the raw features and try to come up with some kind of function. Another issue was that we have a really unbalanced data. So most of the time, people are not dying in the game. So like 99% of the labels were not die. So we have to balance the data to train the network. But the problem is that you have 10 independent outputs. So like normally we would, there's one technique to balance the data set is oversampling, where you just copy the labels which you have less of multiple times. So it's, the probability of selecting both kinds of labels is the same. But because we have 10 independent outputs, it's impossible to balance them all at the same time. So what we do instead is we select one output randomly, balance for that output, and only backpropagate the error from that output. And every training iteration, we randomly select a different output. So how can we evaluate the performance? Because if this data imbalance, accuracy is a really poor measure because it's trivial to get a good accuracy. So instead we can use precision and recall. So precision is the ratio of when we predicted that someone dies, the ratio or the percentage of those cases when they actually die. And recall is when they actually die, what percentage we predicted that they die. There are several other aspects of evaluating. First, this is like a time series prediction, and we have this artificial threshold of 5 seconds window. So it's unreasonable for the network to exactly learn this 5 seconds, and we are not expecting that, because like 5.1 seconds, if the network predicts that someone dies 5.1 seconds before they die, that would be a false prediction according to our evaluation. Another thing to consider is that we are predicting who will die, but our original goal was to predict excitement. So even through we have this kind of measures, it might not. It's difficult to interpret if these measures are what we want or not. So this is the precision recall curve. So we can select the threshold for this binary classification, and these are the precision and recall scores that we can achieve. For example, if we choose a threshold which results in 0.4 precision, that would result in 0.7 recall. So this is really useful for comparing different models, but it's not too intuitive as how this feels. So instead, this is the predictions of the network on a whole match. So and there are some two zoomed-in versions of some small parts of the game. So the red lines are the predictions of the network. So when the red lines are high, the network predicts that the players die. And then where there is this blue K, then the player actually dies. So we can see that the network is very good at predicting if this happens 1 or 2 seconds before. It's every case it predicts a few seconds before it can predict. Sometimes it predicts much longer than that, but there are some cases when it predicts when the player does not die. So this is nice, but it still doesn't really tell us how it feels, how is the quality of the network. So we can see a clip of a game, and here we can see the game on the top, and on the bottom you can see the predictions of the network. Each player have like a speedometer, and if the network predicts that the player is going to die, the speedometer is going to move. And when the player actually dies, it will turn to gray. In this clip, we will follow the player on the very left. The prediction is on the very left, and he's going to be attacked. So the network predicts the attack before it takes any damage. So now the network already predicted he's in trouble, and he died. Here is another clip. The one player is running away, and the network knows he has no chance of running away already. And one big point of our method is team fights. When a team fight happens, it's so chaotic. The network have a hard time following the events, so it can predict that a few seconds before, but it's only like 1 or 2 seconds. So it's not too accurate in team fight scenarios. Right. Thank you for your attention. For the questions, I have some clips to run in the background. Yeah.
So, first very quick question, how do you deal with Meeple?
With what?
Meeple, he's on the, because do you put, for those who don't know, it's a hero that has multiple copies, and any of them die, the hero dies.
Actually,
Are you tracking only the main?
I played more League of Legends than Dota, so no culture.
So did you observe any particular failure mode? So maybe the network is bad at predicting a certain hero will die because it doesn't understand how that hero works, or a certain item low.
Yeah, so we had a few issues. For example, there is this Monkey King who can jump on trees, and that's really confused the model, I believe. And yeah, I'm not sure. There is better people to ask with better domain knowledge. Yeah.
Did you do any ablation studies on which particular features contribute most to the prediction?
Yeah,
Health is going to be.
Yeah, we had three kinds of feature sets. One which had everything. One which didn't have the hero ID, because the hero ID was a lot of features, because it's one-hot encoded. We have more than 100. And one which were really minimal. And even the minimal worked all right, but there are several percent better with the. There is this average precision, which is like a single number performance indicator, and several percent. The medium was several percent better, and which had everything, that was 1% better. So you can actually do a good job with a quite minimal one as well, but adding new features definitely improves performance.
Can I add a follow-up question to that? Because these features, did you also have different features? Because I can imagine that the loss of health is more predictive than pure health.
Yeah, we have had a few historical features, especially the visibility, because the game is quite we almost have every feature, so it's a fully observable environment. So actually you don't need historical data to evaluate the game state. But one thing we cannot consider is the mind of the player. So maybe if the trajectory to this state is different, then a player would act differently. So for this reason, it's really nice to include this kind of difference features. So we had a few. Yeah.
So those clips you're showing now, what determines the camera position in those?
So with the camera position.
So the idea is that you want to maybe focus on where the action is happening. It seems like the camera is already following.
Yeah. So actually, we are using the replay of the Dota 2 client. So you can choose which player you want to follow. You can choose the automatic camera. Yeah, that's one possible application of our model to automatic camera movement. That's definitely an interesting direction. But these clips are just the Dota 2 clients. But
do you know how that works, the auto camera there?
I'm not quite sure. You can choose to follow players or choose. I'm not sure how Dota implemented it.
Thank you.
Thank you.
There's some Rodrigo. Did I pronounce your last name Canaan?
Yes,
And you are from
Brazil.
Brazil? And University of Brazil?
Yeah, no, I'm from NYU. I'm with Julian.
Yes, yeah. I suspected, but I want to make sure.
Is it this cable?
I'm not sure. Probably.
I think, well, I messed up. This port, I think, has a problem. Let's see.
Still, no, it's going.
It just takes a minute. Okay. Okay.
You're ready to begin?
Yes.
Okay. Last paper in this session, presented by Rodrigo Canaan from NYU, and it's about evolving the Hearthstone meta. Please go ahead.
Hi.
I'll indicate 5 minutes.
Thank you. So I'm Rodrigo. It's a pleasure to be here. So the first author of this paper is Fernando, but he couldn't be here. So let's jump to it. I'll first talk about the motivation for this paper. And our motivation is dealing with how AI can help with game balancing. So game balancing is the problem that some games have a lot of different moving parts, a lot of different features, characters that you can choose from, or cards that you can put in your deck. And designers want the game to have a lot of variety of these features, but the players want to win. And so if let loose, the players might focus on, I mean most players at least, they might focus on a very small subset of those and make the game unfun because there's only one or two strategies that have any chance of actually winning in high-level play or at other levels. So the game is balanced for us, like it's a very loose definition, but the game is balanced if there's a reasonable diversity of strategies that can perform well at a certain level. So for example, at the highest competitive level or other skill levels. And it's a very complex and expensive process. You need play testers, you need a whole group to do this if the game is big enough. And how could computational approaches help us do that? And next is why do we choose Hearthstone? So Hearthstone is a very popular game with 100 million players or more. And it presents multiple challenges to AI that we can link to. So there's obviously the challenge of playing the game, which is made hard because there's hidden information, there's stochasticity, there's a large branching factor. There's the challenge of building the decks themselves, which is made hard because there are so many cards. And there's the challenge that is closest to what we're doing here, which is of generating, playtesting, and especially balancing, in this case, existing content. And the game has also a large community interest in the research community. So there's the Cyberstone tool, which is maintained by someone who's in the audience, who's also part of the Hearthstone competition, the winner. So Cyberstone is a framework for simulating the game, and it really helps us here because it's available for us to do a bunch of playtesting with AI agents. So we have two different separate goals here. The first one is that we want to devise and the main one is that we want to devise computational methods to achieve balance in games using Hearthstone as a test bed through sets of balance changes to the existing cards. So nerfs and buffs, if you know the terminology. If you don't, nerf is a bad change, is a change meant to make the card worse, and buff is a good change meant to make it better. And after we've done that, we will try to achieve balance with as few changes as possible, because we don't want to disturb the game environment a lot by changing all of the cards if we can avoid it. And there's a separate set of goals, which I will touch very briefly at the end, which is there are some metrics that the card game community uses to assess the power level of a card, and we want to see how well they correlate with the impact that it has when we nerf that card, both as a matter of the interest in itself, like to see if these metrics work that the community has devised, and also because this could help us target our nerfs better. Like instead of running a whole simulation expensive, if we just measure and they correlate well enough, maybe in the future we can use them to more accurately target our nerfs and buffs. Okay, so this paper is not about directly generating AI to play Hearthstone, and it's not about generating the decks themselves. So we take those as granted. There's some policies in the framework that we're using, the aggro and control strategy in Cyberstone, and we're using agents that from a previous paper, which also take those for granted. And if we consider the metagame that's comprised of these decks that we're considering, how do we balance it through balance changes? And I just said metagame, so let me explain what that is. So metagame has a broad definition that is, and very general, that is the set of factors outside the game rules that affect the game experience. So you could say even things like, there's like the group things, so people think that a certain deck is good, so they will play it a lot, or people think that certain strategies is good, so they will play that way. And there's more subtle factors, so for example, maybe I already know that player and I know that they only play one type of deck. That could also be considered a type of metagaming in the very broad definition. The narrow definition, that's usually called the meta, is the set of decks that's used by the players in a certain a snapshot of the game, and how popular they are, and how well they win against each other. What's the win rate against each other? Sorry, yeah. And this is the object that we're trying to balance. We're trying to balance this meta in the narrow sense. So there's a group of decks. We know how they win against each other, what's the win rate against each other, and we want to make that balanced. Okay, a brief explanation of how the game of Hearthstone works. So it's a game about using minions and spells to make your hero defeat the opponent's hero by reducing their cards. So the game has a lot of moving parts, which if you were here for the CoG competition, you've probably seen. So you have your hero, you have cards in your hand, you have a hero power that you can use every turn. You can equip weapons to attack directly the other players or the other minions, and you can have your own minions on the battlefield. And it's a turn-based game where you just play your cards in the order that you think is going to help you win the most, and you choose the targets for these cards, etc. So here's some example of Hearthstone cards. They are mostly of three types that we're going to consider in this paper. There's minions, which once you play, they stick to the board until they die, and they get to attack every turn and deal damage to other characters. There's spells that have a one-time direct effect, so they can deal damage, they can draw you cards, they can do other more complex things. And there's weapons, which you attack, and they have a number of charges, which is on their left side, which is how often they can attack. And so minions have, all of these cards have the attribute at the top left, that's their mana cost, which is how much they cost to play. And, but minions and weapons also have an attack and a health or durability on the right, which is how durable they are, how long they stay on the battlefield. And so deck building, is as I said, is a very complex challenge. Even if in this paper we restrict ourselves to the classic and basic set, but even with only 140 neutral cards and 25 cards for each specific class, there's still a huge number of possible decks. So if you want to tackle the challenge of deck building, it's not possible to do this exhaustively. And so when a deck becomes unbalanced in the perception of the players and of Blizzard, the maintainer of the game, they sometimes address that through balance changes. There are no nerfs and buffs. So they typically do that by, for example, increasing the mana cost of a card or lowering its attack and health attributes. And these are very easy to represent for us. There are some changes, balance changes, that are a bit harder to represent, so they go into the text of the card and change some of its abilities. We're not dealing with those on this particular experiment. So we're only dealing with balance changes that are changes to health, mana, and attack. So the decks we used were extracted from previous work from some of my co-authors, where they use Map Elites, which is an evolutionary algorithm that searches for a variety of different decks with different characteristics. So it searches for decks with different mana costs and mana variances. And so all the paper is there, the reference. And out of the decks that they came up with, we selected three, one from each of the three classes that we were considering to make our experiments. So we selected one Hunter aggro deck, one Paladin control deck, and one Warlock control from that paper. And once you play these decks against each other, you see that they are very unbalanced. So Hunter loses to both Paladin and Warlock, and Paladin beats everyone. And that's what we're going to try to address on our experiments. So the main thing that we want to do is first ask ourselves, how balanced can we make the metagame by introducing changes to these cards' attributes? And then how do we do so after that while minimizing the number and the severity of those changes? So for the first experiment, our objective was to balance the metagame through changes in the cards' attributes. And again, the balance changes that we're dealing with are very simple to represent. You can think of them as a vector of, for each card is just 3 numbers in the case of minions and weapons. So a change to their mana cost, their attack and health. And spells are even simpler. We're considering just a number because they don't have attack and health. And then you string all the changes. So you can think of a balance patch where you introduce changes to multiple cards at once. You can think them as stringing the individual balance changes of each card. And so you get a huge vector like this, representing all the attributes that we're interested in for all the cards that are in those decks. So this is an example of a possible balance patch. And yeah, it's 180 size vector. And we're applying for each attribute of a change of from -3 to +3. And so this is how we're representing our individuals in our evolutionary approach. Now, how we measure, how we evaluate them, what's their fitness. So we take the vector of matchup win rates for each of them. So this is how they actually pair against each other. And to simplify, we're going to say that we wish that all these matchups were 50-50. And our fitness is basically what's the Euclidean distance from the vector of actual win rates to the ideal 50-50 that we want to minimize. And so if we do this calculation for the current meta, it has a normalized fitness of 0.78 out of 1, so it's very unbalanced, mostly because Hunter loses to everyone almost every time. So we can probably expect we want to change a few of these cards to make Hunter better and Paladin and Warlock worse. So the algorithm as itself is a very simple genetic algorithm, like tournament selection, mutation, 2-point crossover. The details are in the paper. Each generation is 100 individuals, and we play 300 games per individual, so 100 for each matchup. And an individual here, let me remind you, is not a specific deck. We're not evolving decks. Is a batch of balance changes. So an individual is something that says, oh, I will nerf this card by increasing its mana cost by 1, and that card by reducing its health, etc., for every card. So this is the result of the first experiment. So you can see that in very few generations, it finds metagames that are very balanced. This particular individual, that's the same as I showed you, it was our best individual for the first experiment. It has a balanced evaluation of 0.0062, which since we're trying to minimize, it's almost perfectly balanced. All the matchups are all basically 50-50. So, but what we are also interested in is we want to balance the metagame through card changes, but we want to minimize how many changes we want to make. So we introduce a new metric, which is what we're calling the change magnitude. So we're taking into account by how much you're changing each attribute, and we're weighting mana higher. So when mana has a cost of 2 to change, and attack and health has a cost of 1 because of the way these values interact in the game. And so basically we're taking the weighted average of all the changes that we're making by these weights. So ideally we would have these also as close to 0 as possible. So in multi-objective, so the framework that we introduced to address both balance and like minimizing changes is the one of multi-objective evolution, which is widely studied in the literature. So our goal is to minimize both the balance evaluation, so how close those matchups are to 50-50, and the magnitude of the balance changes. And there's obviously a trade-off there, because I could make no changes, and I would have the initial metagames, which is very unbalanced, and I could make a bunch of changes and probably balance it almost perfectly. So what we choose to employ is an SGA, which is introduces the concept of a dominated individual. So the dominated individual is one that doesn't have a particularly good trade-off. You can find other individuals that are better in both metrics simultaneously. And then it creates a hierarchy of which individuals are not dominated by anyone, and then others that are dominated only by those first in the first level, and so on, to rank them during the evolution. And from there, evolutions proceed basically as normal GA. Very similar. And so once you introduce these two different metrics and you apply an SGA, you get these types of results. So we seeded our multi-objective optimization algorithm with n-2 random individuals and 2 special individuals, which is the no-change individual, which is the one here in the bottom right, because it's definitely the best in that particular dimension. It minimizes changes by default. And also the best one from the experiment, which is that one on the left, on the top left, with a magnitude of about 300. So, and this is the, with the starred individuals, the red stars are the ones that are on the Pareto front of the multi-objective optimization. So these are the ones that are not dominated. They represent some sort of good trade-off between the number of changes that you have to make and how much balance you get. And so, in particular, you see that these 3 individuals here on the left, they have very similar number of changes. They're very similar in themselves. They're very close siblings, and they have a fitness in terms of balance that's also very close. And it's possibly there's some noise in there that the ordering between them is not as important because it's very close to 0. It's like below 0.1. But the key thing from our results is that, yeah, if you try to search not only for the best balance, but you include this secondary objective, you can reduce the number of changes by a factor of almost 2, while keeping the balance in a similar range. And then if you are willing to suffer more, a little bit more imbalance, you can get other metagames with less changes even, until you come to the baseline case of no changes, which has no changes. So this is the result for the second batch of experiments. And so I'll very quickly go through the third experiment that we described in our paper. So we took 2 metrics that replay websites use to kind of estimate the power level of a card. So it's the win rate that a card has when it's played and when it's drawn. So out of all the cases that you played a card, how often did you win? And out of all the cases that you drew that card in your hand, that card showed up in your hand, how often did you win? And our hypothesis here that we were trying to test is that these cards, the cards that score higher on these power metrics, were the ones that you want to nerf. And so we took the unmodified control paladin deck, which is the best deck, and we did 30 different runs where in each of them you target each of these cards with a nerf of 1 mana. Like that's 1 mana higher. And then we cross-referenced, like, what's the win rate of the nerfed deck versus what's the power metric of the card that was nerfed, to see if there was any correlation. And so we got almost negligible correlation between the win rate that you get when a card is played. So it makes not that much change which card you nerf with respect to how much it wins when it's played. So that's not a good metric. But when you consider how much a card wins when it's drawn, that's a very good metric for us. That's a much better metric for us to use when determining the nerfs. So basically, the highest the win rate that a card had out of all the cases that it came into your hand, the more the deck suffered if you nerfed it. So as a conclusion, we can achieve near perfect balance if we evolve this sets of balance changes with respect only to the balance. But this might suffer of many changes, and the one way to address that is to introduce a second objective, to do multi-objective search and search for a set of agents that minimize both at the same time. And also we have this, on the third experiment, that a card's win rate when it's drawn seems to be a better metric to use for balancing decisions than its win rate when played. And for future work, through all of these experiments, we're treating the metagame as static, which is not the case in the real game. So if I nerf a card, you're not going to keep playing the same decks. Maybe you trade that card for another card that hasn't been nerfed, or you even scrap your whole deck because it hinged on that card. So we could do other experiments which treat the metagame as dynamic and see which deck emerge. We could use other metrics of balance. So this specific metric that we use is very simple, but it doesn't allow, for example, to exist a rock, paper, scissors dynamics. So we're implicitly saying, which is not a factual statement. It's not necessarily our opinion. It's just the way that we set up. But we're explicitly saying that all matchups should be balanced individual, which is not necessarily the notion that you want. Maybe you could have some sort of rock, paper, scissors going on, and the meta is still balanced. We could, so we could do these other metrics. We could try to introduce more diverse, take into account how diverse these strategies is, so, and also how well these apply to other agents with different policies, and even human play if we have access to repositories of deck lists and replays. So thanks.
Thank you for your work. I really like it. I get two questions. One, actually, you point out in the future work, because like you said, it's actually a repeated phase of balancing and finding a new method to rebalance stuff. So let's skip this one as you pointed out. But the other question, did you consider a variety of cards? Because the problem with nerfs is like you can have 3 ones for 2, like in 7 different variants, yes? Or you nerf a card which is strictly like below other cards that already existed. So like you significantly reduce like these 200 cards to like 100 because you know they are so similar.
Oh, yeah. So I definitely agree, and I think these two questions should be tackled together. Because if we're not allowing for the decks to change in response to a nerf, then it makes no sense to wonder like how many cards are viable, because we're treating the deck list as static. So the first point is that, so in order to do this third point in my future work, I have to first do the first. Yeah, there are a bunch of different nuanced notions of what the ideal metagame balance is. And it might not even take into account just win rate, even if you allow for that those rotations of win rate. It could also take into account like how many cards are in these decks with high win rates. So you could get ever more nuanced versions of your fitness function of how balanced and desirable a metagame is. But the basic underlying idea of using agents to playtest the games and see if they get the result you want, we think apply.
Yeah, so I think like you should
Maybe we can give someone else a chance to ask a question.
We can talk later.
Other questions?
Thank you for mentioning Hearthstone. And my question is, did you check how appropriate the balance changes? For example, if you make attack below the 0 or make it 0, it means the card becomes literally unusable.
No, it's not in the slides because it's more of a technical detail, but we're capping all the values between 0 and 10.
Oh,
so a card's mana cost can be -1, so nonsense like that. It wouldn't work, so we cap it.
One final question?
Someone in the back.
So thanks for the presentation. I currently wonder a bit about these balance changes and thinking about them. So currently you think about in-between decks or in-between hero balance changes, but as a direct follow-up for Jakob, there can also be balance changes considered for in-between cards. So like one card strictly dominates another card. The most extreme case would be a card that costs 1 mana and kills the opponent. Then it will yield a perfect metagame because the win rate of every hero would be 50-50. The first hero who draws the card wins the game.
Yeah.
And how can we incorporate this into the existing system?
Okay, so this is kind of a similar answer to the first question, and it's kind of what we are expecting to get if we were able to incorporate the first 3 points all together. Because then we can incorporate more nuanced notions of balance that take into account not only how the decks play against each other and how well they win, but the compositions of these decks. Like, are they using varied strategies and varied cards? And if we can somehow embed that into our fitness measure, then we can guarantee that we punish metagames of, yeah, every deck is balanced, but every deck is also the same, is also using the same, very similar cards or things like that. We could even take, if we wanted, we could even take into account, like, we want most of the games to finish in a certain range of turns, so we'd start trying to get into the problem of defining fun. But yeah, you can make the fitness of balance as complex as you would like.
Okay, so I think we should stop it here. I'm sure you can answer questions during lunch, as long as he's had his lunch.
Thank you.